In 2005, two researchers were looking at a map of the entire universe. Not a map of stars, but a map of the oldest light in existence. This light, the cosmic microwave background, is the afterglow of the Big Bang. It was captured by a satellite called the Wilkinson Microwave Anisotropy Probe, or MAP. The map showed tiny temperature differences across the sky. These hot and cold spots were the seeds of all the galaxies we see today. The standard theory of the universe, the one every textbook teaches, said these spots should be random. There should be no special direction in the universe. But Kate Land and João Magejo found something else. They published their findings in a paper for Physical Review Letters. They saw that the largest patterns on the map were not random at all. The biggest hot and cold spots seemed to be lined up. They formed a straight line, an axis, across the sky. This was strange enough, but what made it truly bizarre was where this axis pointed. It pointed directly through our own solar system. It was aligned with the plane where Earth and the other planets orbit the sun. There is no reason the largest features of the universe should care about the orientation of our little solar system. The universe should not have a special direction. Magejo, in a moment of dark humor, nicknamed it the Axis of Evil. The name stuck. It was a crack in our understanding of the cosmos. For nearly 2 decades, scientists have tried to explain it. Is it a mistake? Is it a clue to some new physics, or is it something else entirely? The mystery remains, and the explanations get stranger the deeper you go. Number 15. The simplest answer is usually right. The probability of the main alignment in the cosmic microwave background, the one between the quadrupole and octupole modes, was first calculated to be about 1 in 10,000. That seems incredibly unlikely, yet, in a dataset as vast as the CMB sky map, with billions of pixels, we can analyze countless correlations and patterns. The more things you look for, the higher the chance you will find something that looks significant purely by accident. This is known as the look elsewhere effect. The chance of finding some anomaly somewhere in the data is much higher than the chance of finding one specific anomaly you were looking for beforehand. The most boring explanation is often the most likely. The axis of evil could just be a coincidence. It might be a statistical fluke. The universe is vast. We have only one universe to observe. We cannot run the experiment again to see if the patterns come out differently next time. We are stuck with the data we have. When you look at any random pattern long enough, your brain starts to see things. This is called pareidolia. We see faces in clouds and animals in rock formations. Cosmologists, for all their complex mathematics, are not immune to this. They are looking for patterns in the noise of the early universe. Maybe they just found one that isn't really there. The standard model of cosmology is built on the cosmological principle. This principle states that the universe is homogeneous and isotropic. Homogeneous means it is the same everywhere. Isotropic means it looks the same in every direction. If you were in a distant galaxy, the universe would look pretty much the same to you as it does to us. The axis of evil directly challenges the idea of isotropy. It suggests there is a preferred direction, a cosmic North Star, so to speak. If this alignment is just a fluke, then the cosmological principle is safe. Our best model of the universe still holds. This is a very comfortable thought. It means we do not have to throw out decades of work. Scientists have run countless simulations to test this. They create thousands of fake universes on supercomputers based on the standard model. In these simulated universes, the hot and cold spots in the CMB are completely random. Then they check how often an alignment as strong as the one we see in our sky appears by chance. The results are complicated. Some studies say it is very rare, happening in less than 1% of simulations. Others argue that the way the significance is measured is flawed. They say that if you define alignment in slightly different ways, it becomes much more common. The problem is that we are defining the anomaly after we have already seen it. This is a statistical sin. It is like shooting an arrow at a wall and then drawing the bullseye around where it landed. We see an alignment with the plane of our solar system, the ecliptic, But why the ecliptic? Why not an alignment with the plane of our Milky Way galaxy or with the direction of our local supercluster? The fact that we picked out the ecliptic plane makes the result seem more significant than it might be. There are many possible planes and axes one could check for alignment. Finding a match with one of them might not be so surprising after all. It is a cosmic coincidence, a grand but meaningless accident of perspective. This is the explanation of last resort, the one scientists turn to when all others have failed. But in cosmology, where our data is limited to a single sky, it is an explanation that can never be fully ruled out. It is the unsatisfying, simple, and possibly correct answer. Number 14, our instruments are not perfect. The WMAP satellite observed the sky for 9 years, from 2001 to 2010. It measured the temperature of the cosmic microwave background with a precision of a few millionths of a degree. It did this by using differential radiometers. These instruments did not measure the absolute temperature of a spot in the sky. Instead, they measured the tiny difference in temperature between 2 points. WMAP had 2 telescopes that looked at spots of the sky about 141 degrees apart. The satellite spun and processed its orientation to map the entire sky over and over again. This complex scanning strategy was designed to cancel out instrumental noise and errors. But what if it was not perfect? An instrument can have its own subtle biases. These are called systematic errors. They are not random noise, they are patterns that the instrument itself creates and imprints onto the data. Imagine a camera with a tiny, almost invisible smudge on its lens. Every photo it takes will have that smudge. If you did not know about the smudge, you might think you were seeing a real object in the world. For MAP, the smudge could be a tiny imbalance in its radiometers or an unaccounted for source of heat from the spacecraft itself or a slight error in modeling the shape of its telescope beams. The WMAP team spent years analyzing their own data for these kinds of errors. They were incredibly thorough. They looked for anything that could create a false signal. They concluded that their instrument was clean. They believed the signals they saw, including the strange alignments, were genuinely coming from the sky, not from their satellite. But other independent teams of scientists were not so sure. They reanalyzed the raw data. They used different statistical methods. Some of them found evidence for subtle residual errors that correlated with the axis of evil. The alignment is most prominent at the largest scales. These are the quadrupole and octupole moments of the sky map. Think of the quadrupole as dividing the sky into 2 hot and 2 cold regions, like a clover leaf. The octupole divides it into a more complex pattern of 6 or 8 regions. These are the features most sensitive to large-scale systematic errors. A small, persistent error in the way the satellite scanned the sky could, over 9 years of observation, build up into a large fake pattern. One specific concern was the way MAP handled signals from our own galaxy. The Milky Way is a bright source of microwaves that must be carefully removed to see the faint CMB behind it. The process is complex. Scientists have to model the galactic dust and gas and then subtract it from the map. If this model is slightly wrong, it can leave behind a residual signal. Some have argued that this residual signal could be responsible for the alignment. The solar system is located within the plane of the Milky Way, so an error related to the galaxy could potentially create a pattern that appears aligned with us. The scientists who first discovered the axis, Land and Magajo, did their own tests. They tried to reproduce the alignment using models of MAP's known instrumental quirks. They could not do it. They concluded the signal was real, but the debate never really went away. The possibility that we are just seeing a ghost in the machine, an artifact of the very tool we built to look at the universe, is a persistent worry. It is a reminder that our view of the cosmos is always filtered through our technology. And our technology is never perfect. Number 13A, Second Opinion, did not clear things up. The European Space Agency's Planck satellite was launched in 2009. It was the next generation of CMB observatory, a major upgrade from WMA. It was more sensitive, it could see smaller details, it observed the sky in 9 different frequency bands compared to MAPS 5. This gave it a much better ability to distinguish the CMB from foreground contamination like dust in our galaxy. Planck's mission was to create the ultimate map of the early universe, and one of its key goals was to check the strange anomalies that MAP had seen. Everyone hoped Planck would settle the debate. Either it would show the axis of evil was just an error in the MAP data, or it would confirm it beyond any doubt. The first major Planck data release came in 2013. The world's cosmologists held their breath. The Planck map was stunning. It was the most detailed picture of the early universe ever made. And the axis of evil was still there. The alignment of the largest scale patterns was confirmed. The quadrupole and octupole were still strangely lined up with each other. This was a major blow to the idea that the anomaly was just a map instrumental error. Planck was a completely different satellite, built by a different agency with a different design and a different scanning strategy. If both instruments saw the same thing, it was much more likely to be a real feature of the sky. But the story was not that simple. While Planck confirmed the alignment of the quadrupole and octupole with each other, the alignment of this axis with our solar system's ecliptic plane was weaker than in the map data. It was still there, but it was less statistically significant. This made the situation even more confusing. Did Planck confirm the anomaly, or did it weaken it? The answer depended on how you looked at the data. Furthermore, Planck's more sensitive instruments and better foreground cleaning methods changed the map in subtle ways. The exact orientation and strength of the axis of evil shifted slightly. Some scientists argued this was evidence that the entire effect was related to how you subtract the Milky Way's signal. If changing the subtraction method changes the anomaly, maybe the anomaly is just an artifact of that subtraction. Others argued the opposite. They said the core alignment remained even with better data, which proved it was a real cosmological feature. And Planck also confirmed other large-scale anomalies seen by WMEP. It saw the cold spot, a huge, unusually cold patch of the sky. It saw a difference in the statistical properties of the fluctuations between the northern and southern hemispheres of the sky. All these anomalies seem to live on the largest, most puzzling scales. Planck did not get rid of them. In some cases, it made them sharper. So the second opinion did not resolve the issue. It deepened the mystery. It ruled out the simplest explanation of a simple WMA bearer, but it did not provide a clear confirmation that our standard model of cosmology is wrong. Instead, it left cosmologists in a state of limbo. The axis of evil is real, in the sense that it exists in the data from our 2 best telescopes. But its significance and its cause are more uncertain than ever. Planck gave us a better map, but it did not give us a better compass. The universe still seems to have a strange, unexplained direction. Number 12, we are looking through a dirty window. The cosmic microwave background radiation has traveled for 13.8 billion years to reach us. On its long journey, it has passed through a lot of stuff. The space between galaxies is not completely empty, and our own Milky Way galaxy is full of gas, dust, and magnetic fields. All of these things emit their own microwave signals. This is called foreground emission. Before we can study the CMB, we have to meticulously clean our map. It is like trying to take a picture of a distant mountain through a dirty, smudged window. You first have to figure out exactly what the smudges look like, and then digitally remove them from your photo. The primary sources of foreground contamination are synchrotron radiation and thermal dust emission. Synchrotron radiation comes from high-energy electrons spiraling in the galaxy's magnetic fields. It is brightest at lower microwave frequencies. Thermal dust emission comes from tiny grains of interstellar dust that are warmed by starlight. It is brightest at higher frequencies. The CMB has its own unique energy signature. It is a nearly perfect black body spectrum. By observing the sky at many different frequencies, as the Planck satellite did, scientists can separate the different signals. They can build a model of the galactic foregrounds and subtract them from the total map, leaving just the CMB behind. But this process is incredibly difficult and not perfect. Our model of the galaxy is incomplete. We do not know the exact distribution of all the dust and gas. The structure of the galactic magnetic field is very complex. So, when we subtract our model of the foreground, we might be leaving some residual contamination behind. Or we might even be subtracting a part of the real CMB signal by mistake. The axis of evil is a very large-scale, low-amplitude signal. It would only take a very small, large-scale error in the foreground subtraction to create a fake alignment. The alignment is with the ecliptic plane, the plane of our solar system. The solar system itself sits very close to the plane of the Milky Way galaxy. The angle between the two planes is about 60 degrees, so it is plausible that a large-scale error related to the galactic plane could, by a geometric coincidence, project onto the sky in a way that looks like an alignment with the ecliptic plane. Some studies have claimed to show just that. They have created new, more sophisticated models of the galaxy's dust emission. When they use these new models to clean the CMB map, they find that the axis of evil alignment becomes much weaker or disappears entirely. However, other studies, using different methods, come to the opposite conclusion. They find that even with the best possible foreground cleaning, the alignment persists. The problem is that there is no single, universally agreed upon way to do the foreground subtraction. Different teams use different assumptions and different statistical techniques. It is a highly technical and contentious area of research. The mystery of the axis of evil might not be a mystery about the deep universe, but a mystery about our own backyard. You know, it might be a story about our failure to perfectly understand the dust clouds floating a few thousand light years away from us. If so, it is a humbling thought. It means the biggest puzzle in cosmology might be caused by something as mundane as galactic soot. We are trying to see the birth of the universe, but we cannot seem to wipe the window clean enough. For number 11, the dust is closer than we think. The search for contamination that could explain the axis of evil has not just focused on the distant dust of the Milky Way. Some scientists have looked much, much closer to home. They have looked at the dust within our own solar system. Orbiting the sun, mostly between Mars and Jupiter, is the asteroid belt. Over billions of years, collisions between asteroids have created a huge, tenuous cloud of dust. This cloud fills the inner solar system and is concentrated around the plane of the planets, the ecliptic. Sunlight reflects off these tiny dust particles, creating a faint glow in the sky known as the zodiacal light. This zodiacal dust cloud also absorbs sunlight and re-radiates it as heat, which means it emits its own microwave signal. This signal is very faint, much fainter than the emission from the Milky Way. For a long time, it was considered to be a negligible source of contamination for CMB measurements. But the axis of evil is such a subtle effect that even very faint signals could be important. And the key fact about the zodiacal dust cloud is that it is, by its very nature, aligned with the ecliptic plane. If this dust cloud were creating a large-scale pattern on the CMB map, that pattern would automatically have a built-in alignment with the solar system. It is a perfect suspect. The Planck satellite was sensitive enough to detect the thermal emission from this interplanetary dust. The Planck team carefully modeled this emission and subtracted it from their maps. They concluded that while the zodiacal dust is detectable, its contribution is too small and has the wrong shape to explain the axis of evil alignment. Case closed, not quite. Some researchers have argued that the standard models of the zodiacal cloud are too simple. They suggest there could be a much larger, more extended halo of dust around the solar system that we have not properly accounted for. Or perhaps the interaction between the solar wind and this dust creates a more complex emission pattern than we expect. The solar system is a dynamic place. The sun's magnetic field, the solar wind, and the gravitational pull of planets all shape the distribution of dust. In 2021, a team of scientists proposed a new and detailed model of this contamination. They performed complex simulations and argued that the microwave emission from the zodiacal dust, when combined with other subtle effects, could indeed mimic the quadrupole signal seen in the CMB. They claimed that once this effect was properly removed, the alignment with the ecliptic disappeared. This is a very controversial claim. Other experts in the field have disputed their methodology and conclusions. The idea is tantalizing because it is so simple and direct. It connects the anomaly directly to the thing it is aligned with the solar system. It would mean the axis of evil is not a cosmic mystery, but a local weather report. It is a sign of the dust in our own neighborhood, not a feature of the universe at large. It would be another example of how hard it is to see the universe clearly from our vantage point inside a complex and dirty solar system. The debate over this local dust continues. It is a classic scientific detective story trying to distinguish a faint, distant clue from the noise and interference happening right in front of the detective's eyes. For number 10, maybe we got our own speed wrong. The cosmic microwave background is not perfectly uniform, even after you account for the tiny hot and cold spots. There is one huge dominant feature on the map. One half of the sky is slightly hotter than average, and the opposite half is slightly colder. This is called the CMB dipole. It is not a feature of the early universe. It is a result of our own motion. Our solar system, our galaxy, and our entire local group of galaxies are moving through space at a tremendous speed. We are traveling at about 627 kilometers per second relative to the CMB. This motion causes a Doppler shift in the ancient light. The light from the direction we are moving towards is blue shifted, making it appear hotter. The light from the direction we are moving away from is red shifted, making it appear colder. Before cosmologists can study the primordial fluctuations, the seeds of galaxies, they must first subtract this massive dipole signal. The subtraction is a standard, routine part of the data processing. But what if it is not being done perfectly? The dipole is about 1,000 times stronger than the anisotropies cosmologists are interested in. A tiny error in subtracting this huge signal could leave behind a significant residual artifact. And this artifact would, by definition, have a direction associated with our motion. Could this explain the axis of evil? The direction of our motion, the axis of the dipole, is not aligned with the axis of evil. They are quite far apart on the sky, so a simple error in subtracting the main dipole cannot be the answer. However, the situation is more complex. Our motion is not just a simple velocity. The standard model assumes our motion is a pure boost, a straight line velocity, but what if our motion has other components? What if the universe is not just expanding, but also has some large-scale rotation or shear? This would induce more complex distortions in the CMB that are not captured by the simple dipole subtraction. Furthermore, the dipole is not the only kinematic effect. There are other, much more subtle effects caused by our motion that are usually ignored. For example, our motion should modulate the brightness of the fluctuations we see across Thesky, an effect called aberration. It should also affect how gravitational lensing by intervening galaxies distorts the CMB. These effects are tiny, but they do have specific directional signatures. Some researchers have investigated whether an incomplete understanding or incorrect removal of these kinematic effects could be responsible for the apparent alignments. The most radical idea in this vein is that the dipole itself is not entirely due to our motion. A small fraction of the CMB dipole could be intrinsic, meaning it was actually a feature of the early universe. This is a heretical idea in cosmology, as it would imply a massive built-in temperature gradient across the entire observable universe. This would violate the cosmological principle in the most dramatic way possible. If this were true, then our subtraction of the dipole would be wrong. We would be subtracting a real cosmological signal, and this act of incorrect subtraction could create all sorts of spurious patterns and alignments in the residual map. Most cosmologists consider this possibility extremely unlikely. The evidence that the dipole is almost entirely due to our motion is very strong. But in the face of persistent anomalies like the axis of evil, some are willing to reconsider even the most basic assumptions. The puzzle forces scientists to go back and check every step of their calculations. Even something as fundamental as accounting for our own speed through the cosmos is put under the microscope. Number 9. The universe rotates on an unseen axis. The standard model of cosmology is based on the Friedmann-Lemaitre-Robertson-Walker-Fleroux metric. This is a solution to Einstein's equations of general relativity that describes a universe that is perfectly homogeneous and isotropic. It is the mathematical foundation of the Big Bang theory. It assumes the universe is expanding uniformly in all directions, with no overall rotation or shear. But this is an assumption. It is the simplest possible model. What if the universe is more complex? General relativity allows for other types of cosmological solutions. One class of these are the Bianchi models. These models describe universes that are homogeneous but not isotropic. They can have a preferred direction. They can stretch more rapidly in one direction than another, a property called shear. They can also have an overall rotation, a property called vorticity. If we live in a Bianchi universe, then the cosmos would have a built-in axis. A rotating universe would leave a very specific signature on the cosmic microwave background. The photons of the CMB would be dragged along by the spinning spacetime. This would create a spiral pattern of hot and cold spots on the sky. Scientists have searched for such a pattern in the WMAP and Planck data. The constraints are very tight. The data shows that if the universe is rotating, it is doing so extremely slowly. The rotation is so close to zero that, for all practical purposes, we can say the universe is not rotating. However, other types of Bianchi models without rotation are harder to rule out. A universe with shear, for example, would expand at different rates in different directions. This would create a large-scale quadrupole pattern in the CMB temperature. The universe would look slightly hotter in two opposite directions and slightly colder in the two perpendicular directions. This sounds promising, as the axis of evil is fundamentally a puzzle about the CMB quadrupole. The problem is that a simple Bianchi model predicts a very specific type of quadrupole. The quadrupole we observe in our sky does not quite fit the prediction. Furthermore, the standard theory of cosmic inflation, the period of super-fast expansion in the first fraction of a second after the Big Bang, was invented specifically to explain why the universe is so isotropic. Inflation would have stretched any initial anisotropy, any shear or rotation, to enormous scales far beyond our observable horizon. For us to see the effects of a Bianchi universe, inflation would have to have been very short or have worked in a very different way than we currently believe. Despite these challenges, some physicists continue to explore these models. They argue that the axis of evil and other large-scale anomalies are a sign that we need to abandon the simplifying assumption of isotropy. They are trying to build more complex models that can fit the data better than the standard model. For example, some have proposed models where the universe started out highly anisotropic, and inflation just barely lasted long enough to make it almost isotropic, leaving behind a few residual large-scale anomalies as a faint memory of its chaotic beginning. This would be a profound shift in our worldview. We are used to thinking of ourselves as living in a universe without a center or a special direction. A Bianchi universe would change that. It would mean there is a fundamental grain to the fabric of space-time. The laws of physics would be the same everywhere, but the cosmos itself would have a large-scale structure and inherent orientation. The axis of evil might be our first glimpse of this cosmic blueprint. Number 8, the universe is a hall of mirrors. We assume the universe is infinite. Or at least it is so vast that for all practical purposes it might as well be. But this is another assumption we cannot prove. It is possible that the universe is finite. If it is finite, it probably does not have a hard edge. Instead, it would likely wrap around on itself. This concept is called cosmic topology. Think of a 2D analogy. The surface of a sphere is finite but has no edge. If you walk in a straight line, you eventually come back to where you started. The surface of a donut or torus is also finite and has no edge. But its geometry is different. You can travel in a straight line and come back to your starting point from a different direction. Cosmic topology suggests our 3D space could have a similar property. It could be a 3 torus or a more complex shape. If you traveled in a straight line for long enough, you would end up back where you started. If the universe has a finite wrapped around topology, it would create a specific pattern in the cosmic microwave background. We would be seeing the same regions of the early universe from different directions. It would be like living in a hall of mirrors. You would see multiple images of the same objects. In the CMB, this would manifest as pairs of circles on the sky that have identical patterns of hot and cold spots. These are called circles in the sky. The size of these circles would depend on the size and shape of the universe. If the universe is only slightly larger than our observable horizon, we would not be able to see any circles. But if the universe is smaller than our horizon in at least one direction, then the circles should be there in the CMB map. Scientists have spent years searching the map and Planck data for these matching circles. So far, the search has come up empty. There is no statistically significant evidence for any repeating patterns. This suggests that if the universe does have a non-trivial topology, the scale of this topology is larger than the part of the universe we can see. So, how could this relate to the axis of evil? Some specific topological models can produce large-scale anisotropy. For example, a slab topology, where the universe is finite in one dimension but infinite in the other two, would naturally single out a preferred direction. A donut, or 3 torus universe, if the 3 dimensions of the donut were not all the same size, would also have preferred axes. This inherent directionality in the shape of spacetime could be the source of the alignments we see in the CMB. The axis of evil could be telling us about the fundamental shape of our cosmic home. One particularly intriguing model is the Bianchi I torus. This combines the idea of an anisotropic universe with a donut-like topology. Researchers have shown that such a model could potentially explain not just the axis of evil, but also other large-scale anomalies without requiring us to see matching circles. The effects would be more subtle, woven into the overall statistical properties of the CMB map. This explanation remains highly speculative. The lack of any smoking gun evidence, like a clear pair of matching circles, means that cosmic topology is not a mainstream solution to the puzzle. But it is a fascinating possibility. It opens up the mind-bending idea that the vast universe we see is, in a sense, an illusion. We might be seeing the same limited cosmic volume over and over again, like a repeating pattern on a celestial wallpaper. Number 7, a great river pulls everything along. In 2008, a team of astronomers led by Alexander Kashlinsky announced a stunning discovery. They were studying the motion of about 700 galaxy clusters. These are the largest gravitationally bound objects in the universe. They use the subtle way these clusters scatter the cosmic microwave background to measure their velocity. They expected to find that the clusters were moving randomly in different directions. Instead, they found something completely different. They found that all the clusters, stretching across a huge volume of space, seemed to be moving together in the same direction towards a point in the sky between the constellations of Centaurus and Vela. This coherent, large-scale motion was dubbed the dark flow. The speed of this flow was estimated to be between 600 and 1,000 kilometers per second. This is a huge velocity over and above the general expansion of the universe. What could cause such a thing? The researchers proposed that the flow was being caused by the gravitational pull of something massive that lies beyond our observable horizon. The universe we can see is limited by the distance light has had time to travel to us since the Big Bang. There could be enormous structures, superclusters of galaxies or other exotic objects that are so far away we cannot see them directly, but we could feel their gravity. The arc flow could be our local patch of the universe being pulled down a gravitational hill towards one of these unseen cosmic behemoths. This discovery was and remains extremely controversial. The measurements are very difficult to make and are subject to large systematic errors. The Planck satellite team later analyzed their own data on galaxy clusters and claimed they could not confirm the dark flow. They found no evidence for such a coherent, large-scale motion. The original team has disputed the Planck analysis, and the debate is ongoing. But if the dark flow is real, could it be connected to the axis of evil? The direction of the dark flow is in the same general area of the sky as the axis of evil and the CMB cold spot. This could be a coincidence, or it could be a clue that these seemingly separate anomalies are all part of the same physical phenomenon. How could a large-scale flow create an alignment in the CMB? It would not affect the CMB itself, which comes from a much earlier time, but it could affect our measurement of it. A large-scale flow would add another component to our own motion. As we discussed, our motion relative to the CMB creates the dipole. If our overall motion is more complex than a simple straight line, perhaps due to being caught up in a dark flow, then the process of subtracting the kinematic effects from the CMB map could be flawed. This could leave behind a directional artifact. Alternatively, the massive structure causing the dark flow could itself be the source of the anomaly. If there is a huge concentration of mass just over the horizon, its gravity could have influenced the part of the early universe that we now see as our CMB. It could have distorted the initial pattern of fluctuations, creating a preferred direction that points towards it. In this picture, the axis of evil is like a cosmic signpost pointing to the location of an unseen giant. The dark flow idea is exciting because it hints at a universe that is even larger and more structured than we can imagine. It suggests that our entire observable world is just a small part of a much grander cosmic web, and that we are being influenced by forces from beyond the veil of our cosmic horizon. But until the existence of the flow itself is confirmed, its connection to the axis of evil remains pure speculation. Number 6. A giant lens is warping our view. Einstein's theory of general relativity tells us that mass warps spacetime, and when light travels through warped spacetime, its path is bent. This phenomenon is called gravitational lensing. We see it all the time in astronomy. A massive galaxy or cluster of galaxies can act like a cosmic telescope, like bending and magnifying the light from more distant objects behind it. The cosmic microwave background is the most distant light we can see. As it travels towards us for 13.8 billion years, it passes through the entire large-scale structure of the universe. Its path is distorted by the gravity of every galaxy and every cluster it encounters. This weak lensing effect subtly changes the CMB map. It tends to make the hot and cold spots slightly smaller and their shapes slightly distorted. Cosmologists have mapped this lensing effect across the sky. It is a powerful tool for understanding the distribution of matter in the universe, especially dark matter, which we cannot see directly. Could gravitational lensing explain the axis of evil? It is unlikely that the cumulative effect of many randomly distributed galaxies would create a coherent, large-scale alignment. The effect of lensing tends to average out over large areas. However, what if there was a single, truly enormous structure that was doing the lensing? A supercluster of galaxies, or a vast filament of dark matter, far larger than anything we have yet discovered. If such a structure existed, and if it were located at a particular distance from us, it could act as a giant distorting lens. It would stretch and shear the image of the CMB sky. This could potentially take a random isotropic pattern of fluctuations and transform it into one that appears anisotropic from our point of view. It could create a preferred direction, an axis, in the lensed image that we observe. The problem with this idea is that we have not seen any such structure. Astronomers have mapped the distribution of galaxies in our local universe in great detail. There are huge superclusters and vast empty voids, but nothing on the scale that would be required to create an anomaly as large as the axis of evil. If such a lens exists, it would have to be very far away, or be made almost entirely of dark matter, making it very difficult to detect. Another possibility is that the lensing is being done not by matter, but by a gravitational wave. In the first moments of the universe, cosmic inflation would have produced not just density fluctuations, but also ripples in space-time itself, called primordial gravitational waves. These waves would stretch and squeeze space as they propagated. A very long wavelength gravitational wave, one with a wavelength as large as our observable universe, would create a large-scale quadrupole pattern in the CMB. This is a known effect that cosmologists search for. The pattern created by a gravitational wave has a specific signature in the polarization of the CMB light. The Planck satellite and other experiments have searched for this signature. They have not found it. The current limits suggest that primordial gravitational waves did not contribute significantly to the temperature patterns we see on the largest scales. So, this explanation seems unlikely. The idea of a giant lens is a long shot. It requires us to believe in the existence of a cosmic structure larger than anything predicted by our standard models of structure formation. But it is a physically plausible mechanism. It uses known physics general relativity to explain the anomaly. It does not require a revolution in our understanding of the early universe, just a revision of our understanding of the universe's recent history and its contents. Number 5, the universe was born with a compass. In our everyday world, magnetism is a powerful force. The Earth's magnetic field protects us from the solar wind. Magnets run our electric motors and store data on our hard drives, but on cosmic scales, gravity is king. Magnetism is usually considered to be a minor player in the evolution of the universe. But what if that is wrong? What if the universe was born with a large-scale magnetic field? These hypothetical fields are called primordial magnetic fields. They would have been generated in the first moments of the Big Bang, perhaps during, cosmic inflation or during one of the universe's early phase transitions. If they existed, they would have permeated the hot, dense plasma of the early universe. This plasma was made of charged particles like protons and electrons, and magnetic fields exert forces on charged particles. A primordial magnetic field would have had several effects on the cosmic microwave background. First, it would have exerted pressure and tension on the plasma, changing the way sound waves propagated through it. This would alter the pattern of hot and cold spots in the CMB. Second, it would have created specific types of anisotropies. A uniform magnetic field would naturally single out a preferred direction in space. This would break the universe's isotropy and could generate a quadrupole alignment, just like the one seen in the axis of evil. The magnetic field lines would act like a cosmic compass needle, imprinted on the fabric of the early universe. Third, primordial magnetic fields would generate a specific type of CMB polarization signal, known as a B mode. This is the same type of signal that primordial gravitational waves are expected to create. Searches for B modes are ongoing as they are a key test of cosmic inflation. A detection of B modes could be a sign of either gravitational waves or primordial magnetic fields. So, is there any evidence for these fields? The Planck satellite has placed very tight limits on the strength of any large-scale primordial magnetic field. The data shows that if such a field exists, it must be extremely weak, much weaker than the magnetic field of our own galaxy. However, some researchers argue that even a very weak field could be sufficient to seed the magnetic fields we see in galaxies today. It is a major unsolved problem in astrophysics how galaxies got their magnetic fields in the first place. Primordial fields could be the solution. Some scientists have built specific models where a primordial magnetic field is responsible for the axis of evil. They show that you can choose a field with the right strength and orientation to explain the observed alignments. The problem is that these models can feel a bit contrived. They are designed to solve a specific problem, but they do not always emerge naturally from a more fundamental theory. The idea of a magnetized universe is a compelling one. It adds a new ingredient to our cosmological model. But for now, it remains on the fringes of cosmology. There is no direct, unambiguous evidence that primordial magnetic fields exist. They are a potential solution to several problems, including the axis of evil and the origin of galactic magnetism, but they remain a ghost in the cosmological machine. The universe's compass, if it ever existed, is proving very difficult to find. Number 4, we are seeing ghosts of universes past. Sir Roger Penrose, a Nobel laureate and one of the world's most creative physicists, has proposed a radical and beautiful theory of the universe. He calls it conformal cyclic cosmology, or CCC. In the standard Big Bang model, the universe began from a singularity and will expand forever, growing colder and emptier until it eventually suffers a heat death. In Penrose's CCC, this is not the end. It is the beginning of the next universe. The theory relies on a strange property of physics. At the very beginning of the universe, the Big Bang, and at the very end, the heat death, the universe is dominated by particles that have no mass, like photons. In such a universe, the concept of scale, of time, and distance becomes meaningless. Penrose argues that the infinitely large and cold future of one universe becomes mathematically equivalent to the infinitely small and hot beginning of the next. The end of one yawn smoothly transforms into the Big Bang of another. The universe goes through endless cycles of birth, death, and rebirth. This is a mind-bending idea, but it makes a few testable predictions. According to Penrose, some information from the previous eon could leak through into our own. One source of this information would be the supermassive black holes that will dominate the very late universe. According to Stephen Hawking, black holes are not completely black. They slowly evaporate over vast timescales by emitting Hawking radiation. In the final moments of their evaporation, they release a huge burst of energy. In CCC, the final evaporation of a supermassive black hole in the previous eon would leave a mark on our cosmic microwave background. It would appear as a slightly warm circular spot with a very specific temperature profile. Penrose and his collaborators have claimed to have found evidence for these Hawking points in the MAP and Planck data. Their claims are highly controversial and have been disputed by most other cosmologists who argue that the spots are just random fluctuations in the CMB. How does this relate to the axis of evil? Penrose has suggested that the axis itself could be a remnant of something from the previous eon. Perhaps a collision between two supermassive black holes or some other cataclysmic event created a gravitational wave signal so powerful that its ripples were able to pass through the crossover from one eon to the next. This could have imprinted a large-scale directional feature, a scar, onto the new Big Bang. This is among the most speculative of all the explanations for the anomaly. It requires us to accept a whole new, unproven cosmology. It relies on the existence of unconfirmed Hawking points and other theoretical constructs. But it is also one of the most profound. It suggests the axis of evil is not an error, not a local contaminant, and not even a feature of our universe alone. It would be a ghost from a previous existence, a message in a bottle from a cosmos that lived and died before our own. It would mean that the most puzzling features of our sky are telling us that our Big Bang was not the beginning, but just another chapter in an eternal cosmic story. Number 3, the first moment of creation was flawed. The theory of cosmic inflation was developed in the early 1980s to solve several major problems with the standard Big Bang model. It proposes that in the first tiny fraction of a second of its existence, the universe underwent a period of hyper-accelerated expansion. It grew from smaller than an atom to larger than a galaxy in an instant. This incredible stretching is what made the universe so big, so flat, and so uniform. Inflation took any initial wrinkles or bumps in space-time and smoothed them out completely. It also provides the origin story for the hot and cold spots in the CMB. Tiny quantum fluctuations in the energy field that drove inflation, the inflaton field, were stretched to astronomical sizes. These quantum jitters became the seeds for all the structure in the universe. The standard model of inflation predicts that these fluctuations should be perfectly random and isotropic. The process of inflation is supposed to be the ultimate eraser of any preferred direction. So, if the axis of evil is a real cosmological feature, it presents a major challenge to the standard picture of inflation. It suggests that the first moment of creation was not as simple or as symmetric as we thought. How could this be? Perhaps the inflaton was not a simple single energy field. Maybe it was a more complex field, or there were multiple inflaton fields interacting with each other. In such a model, it is possible for the process of inflation to have a built-in directionality. The fields could have rolled down their potential hill in a way that was not the same in all directions. This could have imprinted a large-scale anisotropic pattern onto the quantum fluctuations. Another possibility is that inflation did not last long enough. The standard model assumes inflation lasted for at least 60 folds, which means the universe expanded by a factor of e raised to the power of 60A1, followed by about 26 zeros. This is more than enough to smooth out any initial anisotropies, but what if inflation only lasted for, say, 55 e-folds? This would be just enough to solve the main problems of the Big Bang model, but it might not have been enough to completely erase the memory of the pre-inflationary universe. If the universe before inflation was highly anisotropic, a shorter period of inflation could have left behind a residual, large-scale alignment like the axis of evil. These non-standard inflation models are more complex than the simple, single-field models that are most popular. They often require more fine-tuning to get them to work, but they are being taken more seriously in light of the persistent CMB anomalies. The axis of evil could be our most direct clue about the physics of the universe's first yoctosecond. This would be a huge discovery. Inflation is the bedrock of modern cosmology, but we still have no direct experimental proof of it. We do not know what the inflaton field was or what energy scale it operated at. The anomalies in the CMB could be the key to unlocking this mystery. They might be telling us that the process that kick-started our universe was more complicated and more interesting than our simplest theories had led us to believe. The flaw was not a mistake, but a feature, a clue to a deeper level of physics. Number 2, there are cracks in the fabric of space-time. As the early universe expanded and cooled, it is thought to have gone through a series of phase transitions, similar to how water freezes into ice. In some theories of particle physics, these phase transitions could have left behind topological defects. These would be stable remnant structures from the early universe, like cracks or faults in the fabric of space-time itself. There are several types of possible defects. A monopole would be a point-like defect, a particle with a single magnetic charge. A cosmic string would be a one-dimensional defect, an incredibly thin but massive line of trapped energy stretching across vast distances. A domain wall would be a two-dimensional defect, a giant sheet of energy. If these defects were formed, they would still be around today. A cosmic string, for example, would be thinner than an atomic nucleus, but would have an immense density. A string stretching across the observable universe could contain the mass of a galaxy. These objects would have significant gravitational effects. As a cosmic string moved through space, it would warp the space-time around it. Light passing on either side of the string would be bent, creating a distinctive lensing signature. It would produce a line of double images of distant galaxies, A cosmic string would also leave a mark on the cosmic microwave background. As the string moved through the early universe, it would create a wake in the plasma. This would show up as a long, thin line of temperature difference in the CMB map. Scientists have searched the Planck data for these linear discontinuities. They have found a few intriguing candidates, but nothing that has been confirmed as a definite cosmic string. How could a defect explain the axis of evil? The alignment is a large-scale planar or axial feature, not a thin line. A single cosmic string would not do it. But perhaps a whole network of strings or a large domain wall could create a large-scale anisotropy. A domain wall, a giant 2D sheet, would, by its very nature, create a preferred plane in the universe. However, domain walls are generally considered to be cosmologically disastrous. A single domain wall stretching across the universe would have so much mass that it would dominate the cosmic expansion and contradict our observations. More complex theories like string theory predict the existence of cosmic superstrings or branes, higher dimensional versions of domain walls. The physics of these objects is not well understood. It is possible that they could have more subtle effects that could generate large-scale alignments in the CMB without being as obvious or as problematic as a simple domain wall. For example, some have proposed that a nearby cosmic string could be responsible for the CMB cold spot. The gravitational pull of the string would create a cold line, and its oscillating motion could create a colder region at its center. If the cold spot is part of the larger axis of evil alignment, then a defect could be a candidate for the common cause. This explanation takes us to the frontiers of theoretical physics. Cosmic strings and domain walls are not a prediction of the standard model of particle physics. They are predicted by more speculative, grand, unified theories that try to unite the fundamental forces of nature. Finding evidence for a cosmic defect in the CMB map would not only solve the axis of evil puzzle, it would be a revolutionary discovery, providing the first direct evidence for physics beyond the standard model. It would mean the cracks in our sky are literal cracks in space-time. Number 1. The cold spot is part of the conspiracy. One of the most famous anomalies in the cosmic microwave background is the cold spot. It is a large, unusually cold patch of the sky in the constellation Eridanus. It is not just slightly colder than average, it is a major statistical outlier. The chance of such a large and cold spot appearing in a random Gaussian sky is estimated to be less than 1 in 1000. It is a genuine puzzle. For a long time, the cold spot was studied as a separate mystery from the axis of evil. But then astronomers noticed something odd. The cold spot lies directly on the axis of evil. The axis, defined by the alignment of the largest hot and cold patterns on the sky, passes right through this other major anomaly. Is this a coincidence? Or is it a sign that the two anomalies have a common origin? The probability of these two very rare anomalies lining up by chance is extremely low. It strongly suggests they are physically related. This makes the whole puzzle much harder to dismiss as a simple statistical fluke. So, what could cause both the cold spot and the axis of evil? One leading explanation for the cold spot is that it is caused by a supervoid. This would be an enormous, unusually empty region of space, located in the direction of the cold spot. A supervoid would be hundreds of millions of light years across, and would contain far fewer galaxies than an average region of space. How does a void create a cold spot in the CMB? It is a subtle gravitational effect called the integrated Sachs-Wolf ISW effect. As a CMB photon enters a large void, it gains energy as it falls into the void's shallow gravitational well. As it climbs back out, it should lose the same amount of energy, but in an accelerating universe, which ours is, thanks to dark energy, the void is stretching and becoming shallower while the photon is passing through it. This means the photon does not have to climb as far to get out as it fell to get in. The net result is that the photon leaves the void with slightly more energy than it had when it entered. And This would create a hot spot, not a cold one. However, more complex models show that under certain conditions, a void can indeed produce a cold spot. Astronomers have searched for a supervoid in the direction of the cold spot, and they found one. It is called the Eridanus supervoid. It is one of the largest structures ever discovered in the universe. The problem is that detailed calculations show this supervoid is not large enough or empty enough to explain the full coldness of the cold spot. It can only account for about 10 to 20% of the observed temperature drop. The cold spot seems to be much colder than the supervoid can explain. This has led to more exotic explanations. Perhaps the cold spot is the gravitational signature of a cosmic texture, a type of topological defect. Or perhaps it is a bruise on our universe left by a collision with another bubble universe in the context of the multiverse. If the supervoid is responsible for the cold spot, could it also explain the axis of evil? It is hard to see how a single void is a roughly spherical structure. It would not create a large-scale axial alignment across the entire sky. But perhaps the Eridanus supervoid is not alone. Maybe it is just one part of a much larger elongated structure, a superfilament or superwall. If our universe contains such a colossal non-spherical structure, its gravitational effects could potentially create both a localized cold spot and a large-scale alignment. The connection between the cold spot and the axis of evil elevates the entire problem. It ties together multiple independent anomalies into a single coherent mystery. It is no longer just about a strange alignment. It is about a grand, overarching pattern on the sky that defies our simplest models. It suggests that there is something out there, something big that we do not understand. The cold spot and the axis might be two different shadows cast by the same unknown object, a hint of new physics waiting to be discovered.